haven't done it.
Talking about.
How do you do this? How do you change bases? We're not going to worry about that, okay?
Google it, it'll do it.
Well, here's the thing.
There's a modern calculator that does it for you. You don't
Yeah,
have
that's
to
true.
look at it.
That's true. Well, I don't know. Can you do all bases for log?
Yeah. See, I got it before, as long as you have the new stock.
As long as it's in type.
Okay, all right.
You know.
But here's the point. Is the growth rate on this going to be any different than the growth rate on this?
No.
Because why? Because if you want to convert from one log to another, it's a constant factor that's going to be the difference between those two. So you don't have to worry about the bases and all that stuff, okay? That's for my 421 class where students really hate it because they haven't looked at logarithms, and maybe not as long as you, Tony, but for a while. But just be aware that you know the difference. You can compare these two things and tell me that this is going to grow faster than this is going to. Okay. And I've got a chart of it here in a second to show you kind of the relative. In fact, right here. So we have the relative growths and what we talked about. So again, n factorial is going to be the worst. Okay. And the type of problems that we're going to be looking at or dealing with in programs. 2 to the n comes up next, which is exponential. And then we have our polynomial. Those are coming up next. And then we have our cubic, our quadratic, and then we have our n square root of n, which is going to have a faster growth rate than our n log n. Okay. All right. Square roots are going to grow more quickly than logarithms. Yeah. Yes, they're from fast. Well, this is going to be the biggest, greatest, and this is going to be the slowest or the smallest growth rates. And then we have n, square root of n, then log n, and then constant. So what if we have this? What if we have t of n is equal to 26?
Can I ask you a question for the non?
Yeah, just a second. Let me just answer this real quick, if you don't mind. What is that going to be?
24. It's 1.
So how do we write that, you know? We just do 1, okay? All right. Alicia, yeah, you had a question?
So if its growth rate is faster, does that make the program run faster or slower?
It's going to run slower in general.
Okay. Because you're putting.
Because your growth rate, because, so look at it like this. If you had a graph that looks like this, or one that looks like this,
So that.
this has a slower growth rate, so you'd want something that looks like this. You want slower is better, right? Because if you have, well, if you have a really large amount of data,
Yeah.
and I actually have another slide that'll show you that. If you have a large amount of data and your growth rate is really fast. In other words, for every little bit that you're changing n over here,
Yeah.
it goes way up. It's going to take that much longer to do.
Okay.
It's like the Asian
Yeah, Andrew?
ones.
So that would be like a loop and a loop and a loop, where it runs over and over and over and it doesn't get anywhere.
It could be in a sense, yeah, it could be, yeah. Catherine?
So when you're talking about growth rate, you're talking about the amount of data or the.
What I'm talking about is n changes, the size of your data increases. The function, your f of n, is going to go up, okay?
Okay.
So this is going up really fast as n changes, because this is your n, right?
So it's essentially just the slope.
Essentially, yeah.
I saw it as just executions, how many executions it takes for a certain
Yeah, that's basically what it is.
scenario.
Yeah, our f of n is in terms of the number of executions that's going to take in terms of n. Yeah, absolutely. It's the same idea.
Yeah, all right.
Okay. Let's talk about each one of these real quick and give examples. Then I'll show you a chart that actually, I think will go to Alicia's point in a second. So we have constant time. How many times is this going to be executed? One time. Let's say I have 10 statements, and they're all like assignment statements or something like that. What would the growth rate be in that case? It would still be 1, right? Because it's within a constant factor of 1, right? It's not going to matter the size. What about here? Kimberly, what do you think here? What's the predominant thing that's going to be happening here, do you think? What's going to take the most time?
Setting the elements to the values.
Okay, well, it's actually checking it, it's not setting it. So it's, what you want to do is you want to look for for loops, essentially, or some type of loop, and see if you can count how many times that's going to happen. So in terms of the size, how many times is this loop going to execute?
In times.
Or yeah, right, exactly. It's going to be n times, right? Okay. So what is the big O going to be in this case? Yeah, big O of n, right? Now, well, here's the question I have for you. Okay, this is going to execute every time the loop is executed. This is going to be checked n times. How many times is this going to be executed?
Every time it's true.
How many times is it going to be true?
Once.
Maybe,
Yeah.
maybe. What if it's never true? At most, it's gonna happen once, right? Yeah.
Yeah, it's either gonna return true, or it's gonna return false, so it's constant, like there's gonna be a cap of how many times we return something, right?
Right.
So if
So
it's,
constant.
it's either gonna return at most n times, because you're gonna have either true or false, there's never gonna be a combination, right?
Right, exactly. Now, we said this is going to execute n times. Is that necessarily true? No, it's not, right? Because we're going to jump out of this loop as soon as this happens to be true.
Oh, yeah.
What would be the best case scenario? It's the first element. Is that the assumption we want to make? Well, what should we do? Should we make it an average? You know, like half the time?
No, you gotta go up or down.
We want upper bounds, right? And even if we did say, okay, so if we had to go through the list n over 2 times, guess what? N over 2 is still in big O of n, okay? We'd have to be assured that this is going to be some constant time, amount of time that's going to take, and that we can't assume that. So we usually assume that this is going to be executed as few times as possible. That's the worst case. Best case would be the first thing we do. Worst case is that this is the last, or it doesn't happen at all, right? That we go to this, right? Okay. So that's how this analysis of algorithms can get a little hairy, you know. And it depends on the situation. Maybe this is going to happen quite a bit, you know. But in this case, what we're talking about is worst case scenario. Quadratic time, we looked at examples of this, and essentially what it is nested for loops. And you can have deeper nesting. You can have, you know, n cubed or n to the 4th. If you have for loop within a for loop within a for loop within a for loop. Like for instance, this one right here. Both of these for loops are going to go n times. This is going to be executed n times. How many times or n squared times, I'm sorry, because it's going to do this outer loop and then here, but this is going to be n squared. How many times is this going to be executed?
And
N, right?
Yeah.
Because every time that this executes, this is going to be executed, so that's n times. But anyways, so the total, if we want to look at it that way, would be this.
is it n squared plus n?
And I'm going to do it, I'm going to simplify it. I'm not going to worry about,
N squared plus n.
I'm not going to worry.
Times n.
Okay, so let's look at, let's dissect this real quick.
Because we multiplied it earlier. That was because.
So the outer for loop, we're going to do that initialization once, right?
N squared plus n.
We're going to do the comparison n plus 1 times, and then we're going to update n plus 1 n times. Then we're going to do another initialization once within this for loop. So how many, technically, let's just think about this for loop by itself, then we're going to worry about it doing it n times, okay? This is going to be n plus 1, and this will be n, right? Now, this is outside of this for loop, so this would be what? This other statement, this sys out, right? So this is going to be executed n times along with the inner for loop. And so technically the math would be what? It would be, we're going to execute this n times, this n times n plus 1 times, right? And then this n times n times. Okay? The outer statements are going to be executed once, plus n plus 1, plus n. And then we have this one right here, which is going to be executed n times as well, right? And so our T of n, if we added it all up, would be equal to what? We got 1, 2, 2, right? We've got an n squared here, n squared here.
Is that including the sys out that brings the star? It's on the.
Oh, we need that as well. Yep, you're right. We need to do that as well. So that's going to be.
Yeah.
times n squared. Yep. So this is actually 3n squared. Thank you. So we've got this, we've got this, and we've got this. Then we're left with 1, 2, 3, 4, 5n, right? Plus 2. Okay? All right? Does everybody see that? And then we get rid of the lower order terms. We get rid of the constants, so this is going to be in big O of n squared.
We don't do the plus n.
Right? So that, again, that's quadratic term. Exponential, I'm not going to spend a lot of time on this, just be aware that it's stuff like this where you're doing a Fibonacci number. Right?
Yeah.
Yeah.
You're watching.
All right. Logarithmic time. So this is going to be a little less intuitive because I think most of us can understand n squared, and even maybe log n. Well, not really log n in terms of this because you think, what kind of for loop goes log n times? So the example we're going to use is binary search. And this is something we're going to be introduced to later in the semester. After we talk about our abstract data types, we're going to talk about searching and sorting. This is a classic example of a search. So the idea is this. We're given a list, an array of numbers. Now, the one caveat to a binary search is that all of the values have to be sorted, okay? We have to assume they're sorted, otherwise it doesn't work. So, okay? So what you do is this. So we take the middle value, and this happens to be an even number of values, so we just, arbitrarily either round down or round up. So we just look at the middle value, and let's say that we're looking for the value of 7, or we're looking for the value of 20, okay? That's what we're looking for in our list. So we look at the middle value. We compare it to the value we're looking for. And we know that it's greater than that. So what do we know about where to look for 20 now? We just cut out over half the list, right? We don't have to look at that part. It's not there. Then we're going to go to the next part of the list. It's greater than that, so guess what? We just got rid of some more values. We're going to go to this one. We know that it got rid of that value, and then we're going to look here, and then we know that what? It's not in the list. So algorithms that do this, where you take the problem of a given size, and you divide it in half, 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 that's logarithmic. Okay? We're going to look at that a little bit more closely later on, but that's how we get this logarithmic time. When you take the problem and you divide it in half. So you have something that looks like this. As n grows, your curve's going to level off. You're going to keep dividing it out at some point, right? And it's eventually going to almost get flat. This is the code for it. Don't worry about that. It's just showing up there for illustrative purposes. Don't worry about that. We already talked about this. So total remember that for loop we had where we were totaling up things? Where we had the growth rate, which was what? 3n plus 4. So what is that going to be in here? Let me see. Showing Boston is not here. Heston. Yeah. So what would be the big N for that? It'd be A, right? Big O of N. Okay. Here's another example of a dominance where it seems like, okay, it seems like n squared would be big, it's being divided by 10,000. It would seem like this would be bigger than that, right? Well, it is up to a certain point. All right? So that's why I'm going to show you this graph real quick. It kind of gives you an idea of what's going on here. This is n squared over 10,000. It is less than the 2 log base 10 of n, I should put that down there, plus 10,000. Until what? Until you get to this point right here. This would be our n naught. After this point and further and beyond, it's going to have a greater growth rate. And that's what we're talking about. We don't care that this is 11,000, whatever it is. We're talking about billions of items. Okay? Yeah, Alicia.
So if you know, basically what this does is if you know the size of your data set and perhaps how much it might grow,
Yeah.
then you can create your program to be within a certain range to run more efficiently or not.
Yeah, well, what we're doing right now is we're looking at what is known as upper bound. So what we're saying is things get really, really large. This is the worst it's going to get, okay? We know that this is eventually going to be the worst we can get. But if we do know that our data set is less than 80,000, we can say, well, what's the point of that? You know, maybe the algorithm that runs in this time takes a lot of work to get it to, you know, to write it. You know, it's really hard to write efficient code that does this. This is easy. And I know that all my data is going to be less than this. You might want to do that, okay? That's one of those things where it's a trade-off. But that's why we compare these things, so we can look and see what is going to be worse. And sometimes it makes sense to use the less efficient algorithm depending on the data that we're using, and maybe the range of values and stuff like that. Okay. All right, in comparing grades, that's what we already did. This is basically you look at growth rates. And this is I think this gets back to Alicia's question earlier. If we have something that's running, and the assumption here is that n is 100,000, and our processor speed is what? It's 1,000 operations, or 1 billion operations per second. About a gigahertz, right? Log n takes a really, really short period of time. To the end, we're not going to be around. We're not going to be around until the end of the fourth. Kids start doing this stuff. And that's not that big, right? I mean, this is like 4 nested loops. Even end of the 3, I don't know what 11 days for this thing to go on. I mean, people have a hard enough problem waiting 11 seconds, right? So yeah, okay, maybe I'll wait around for that. And then we're getting into more reasonable numbers down here, but I mean, that's the whole point. We want to be able to say, okay, if I've got something that's running log n as opposed to the end, I'm going to go with this every day. I can't necessarily even do it for any kind of data sets, anything greater than 1 bit, right? Okay, so that's why we do this. One more example. So Sam, the other Sam, who's he? The other guy, Sam. We got nested for loops. What do you think the big O of this one's going to be? It isn't.
You said, what did I think?
Okay. Now let's look at it closely. Let's just set our value of row and column to some numbers, okay? Let's just say we're going to do 3, okay? Let's say that row is equal to 3 and column or col is equal to 3. How many times is that outer for loop going to execute, Sam?
9. Oh, the outer.
Well, all together, you're right, okay? Because this outer for loop is going to start at n minus 1, or row minus 1. It's going to do it for row, and it's going to do it for row plus 1. 3 times. Col is the same way. Minus 1, col plus 1. So altogether you're going to do, again, worst case, we're going to assume that this is always executed, so this thing's going to execute 9 times. So you have to be careful. Just because it has a for loop in there, or nested for loops, doesn't necessarily mean it's going to be quadratic, okay? This would be constant time. Because no matter the size of our input, this is going to execute 9 times. Which is B, yeah. No, I'm sorry, A. It's A. Constant time. All right. Let's practice this a little bit.
So if it's a plus 1 or a minus 1 or
all right, I want you to work in groups. It's up to you, just find a partner or whatever.
I don't understand.
Yes.
Go back.
Okay.
So if it's row minus 1 or row plus 1, it's automatically 9? Where did you come up with 9?
Okay, I'll slow it. I'll go back.
Like,
The magic happens here.
That's okay. It's all right. So
It's going to do row minus 1, row, and row plus 1, and then it'll do col
okay,
minus
so we're
1,
going to
col,
set,
and col
okay,
plus 1.
so R is equal to what? Is equal to R minus 1, right?
correct.
Yeah.
Let's say that is equal to, row is equal to 3, so R is going to be equal to 3. C is going to be equal to 3 as well.
Okay, multiplied.
Okay, so the first one, the inner one, we're going to, I'm sorry, it's going to be minus 1, my bad. So it's going to be 2. All right, so let's just do the inner one, okay, just to see, and then the outer one works exactly the same way. So it's going to be set to 2. We're going to increment it. It's gonna be set to 3.